In video 3 of my Basic Electricity series, I explained how there are 6 ways to separate positive and negative charges, creating potential difference, the force that drives current flow and powers all electrical devices. Of those, 2 are responsible for the vast majority of electrical energy created worldwide: magnetism and light. Of the 2, magnetism is the major source of electrical energy. By far, the majority of electricity is generated by spinning a magnet inside a coil of wires to separate charges. Solar energy is growing rapidly, and I believe it will eventually become the primary source of our energy needs. But it's not right now, and won't be for years. Like it or not, we're stuck with spinning magnets for a while. Let's take a look at how that's done. Most commercial generators are 3-phase units, meaning they have 3 separate sets of stationary windings arranged around the inside of the generator casing. As the magnet spins, potential difference is created in those windings separately, 120 degrees apart. Why do we do that? Well, it makes things simpler and cheaper. What did I say? Yes, it is simpler and cheaper to use 3 phases. There's a video on my channel called, not surprisingly, 3-phase electricity that explains the idea in detail, but I'll summarize here. For reasons that involve surface area and cooling, more current can be carried in 3 small wires than 1 big one. It takes less material to transmit a given quantity of current with 3 small wires than it would to carry the same amount of current in 1 big one. For long-distance transmission, the material difference is significant. Large generators and motors use magnetic fields to do their work. Very strong magnetic fields. By splitting the activity into 3 evenly spaced windings, the strain is distributed and smoothed out. 3-phase machines run with less vibration and stress than single-phase machines. By their nature, single-phase motors are difficult to start. The opposing magnetic fields that cause rotation just switch back and forth. It's a minor issue in small motors. Their tiny inertia is overcome with relatively simple wiring tricks. But large motors are another thing. Using 3 phases that arrive 120 degrees apart creates a rotating field around the motor shaft that drags it forward and gets it up to speed. A 3-phase supply makes large motors easier to start. And that's why we have 3 phases, not 4 or 5 or more. 3 is the minimum to make a rotating field. More wouldn't help and would cost more. If we need to make DC out of AC, and some customers require that, we do it by cutting off half the AC cycle. You get a smoother conversion using 3 phases. And finally, there's this. Combining the 3 phases in different ways allows flexibility in voltage supply to customers and circuit protection choices. So, we've established that we're spinning the magnet inside 3 sets of wires. Again, how do we do that? Roughly 80% of the time, steam is used to drive a turbine and spin the magnet. A steam cycle uses a heat source to boil a fluid, usually water, pipe the steam to a turbine, which is connected to the magnet in the generator. The steam is condensed after passing through the turbine, then pumped back into the boiler to be turned into steam again. In this cycle, from 25 to 50% of the heat energy supplied to the water gets turned into electricity. The rest is a heat loss through the cycle. That heat comes from a variety of sources. One of the primaries is coal. About 40% of worldwide generation is coal-fired. In most coal plants, Mined coal is ground into a fine powder and blown into the boiler, where it is ignited and burns, heating water in the walls of the boiler. Steam is drawn off the top, heated further, and delivered to the turbine. Oil can also be used as a heat source in the steam cycle. It's generally a low grade of oil that has to be heated to almost 200 degrees so it can be easily pumped. It's sprayed into the boiler and ignited, where it burns and passes heat on to the water in the boiler walls. Oil currently only makes up about 2% of worldwide generation. Lighter oils, similar to kerosene, are used to fuel gas turbine generators, which are used in a couple of ways in generation cycles. A gas turbine generator is essentially a jet engine, using the force of its exhaust to spin the blades of a turbine and rotate a magnet inside a coil of wires. These can be standalone packaged units, placed on site at substations or generator plants to add megawatts quickly when needed. Because they don't include all the complex support systems of a normal steam cycle, they can be started quickly and are treated as spinning reserve, available in minutes, even when shut down. By themselves, they're not very efficient. There's a lot of heat loss, and usually these units turn only about 25% of the heating value of the fuel into electricity. But they can be made a part of what are called combined cycle units, where they are used as the heat source to a steam boiler. In this type of unit, the gas turbine takes the place of the fans in a typical boiler. The exhaust from a gas turbine runs about 1500 degrees Fahrenheit, over 800 degrees Celsius, so if it is directed into a boiler designed for it, sometimes with just a bit of supplemental firing, it can boil water and make steam to drive a turbine. In these units, there is the generation from the gas turbine plus generation from the steam turbine. By capturing the heat that would be lost in the exhaust and turning it into more generation, these units are up to 50% efficient at turning fuel energy into electricity. Conventional coal or oil-burning units can approach, but usually fall short, of 40% efficiency. That 10 to 15% jump represents a huge savings in fuel cost per generated megawatt. Combined cycle units are driving older single-cycle oil and coal-fired units out of business. They can't compete. Natural gas is also used as a fuel in both steam and gas turbine cycles. Its wide availability, easy transport, low cost, and clean burning characteristics make it currently the most popular fuel for new steam cycle installations, particularly in countries with strict environmental protection laws. However, all of these, coal, oil, and natural gas, are of course fossil fuels. They come from carbon-based material sequestered underground for millions of years. Extracting and burning them releases that carbon back into the atmosphere. Atmospheric carbon increase, in the form of CO2, is linked to increases in global temperatures, with as yet unknown consequences for weather patterns and climate trends. To understand, it might be helpful to look at the process from the standpoint of chemistry. A boiler that burns fossil fuel, whether it's coal, oil, or natural gas, is simply a big vat where a chemical reaction occurs. We add carbon, C, and hydrogen, H, from the fuel, oxygen, O, from the air, and ignite the mixture to speed up the reaction. The products of the reaction? CO2 and H2O. That's right, a boiler is a carbon dioxide and water production facility that gives off heat as a byproduct. That cloud over the stack at a power plant? It's not smoke. It's water vapor. Water created by the combustion process condensing as it hits cooler air above the stack. You don't see the CO2, but it's there also. We are conducting a giant, uncontrolled chemistry experiment, and our lab is the planet we live on. Exciting times, eh? There's another steam cycle system that doesn't suffer from the fossil fuel issues because its heat source is the energy released when atoms are split apart. The pressurized water reactor is the most common type. Nuclear-powered generating units, all types, produce about 11% of the world's electricity. In a PWR, small pellets of enriched uranium are packed into fuel rods, assembled into grids, and loaded into a reinforced vessel. The assemblies are arranged and spaced so that an injection of additional particles causes atoms to split, and the constituents strike additional atoms, causing them to split, and so on in what's called a chain reaction. The high energies of the released particles as they collide with surrounding atoms cause them to vibrate, and that's manifested as an increase in temperature. Control rods absorb some of the particles and are used to control the rate of heat release. The fuel assemblies are surrounded by water under high pressure, so it doesn't boil as its temperature increases. This hot water is pumped to an adjacent heat exchanger, where some of the energy is given up to water at a lower pressure, allowing it to boil and be piped off to drive a turbine and generator. This secondary side of the PWR is very similar to a conventional boiler unit, with similar supporting systems. There are numerous reactor and system designs, each with its own set of positive and negative features. Nuclear power remains a controversial topic worldwide. The two main issues with nuclear energy are safe control and disposal of waste. The typical reactor contains the equivalent of several thousand coal cars of energy. Coal, gas, and oil plants have only the fuel in them that is being burned at that instant. The supply is easy to shut off. The difficulty of containing the reaction and controlling the heat release raises the potential for problems, as has been proven in several well-publicized incidents. In addition, when the heat-producing capability of the fuel assemblies drops below a certain point, they must be replaced. The spent fuel is still radioactive and will remain so for many years. It must be stored and monitored safely. There is currently no central facility for doing that. Spent fuel remains on site at most plants, where it requires extensive monitoring, testing, and security. Alternate nuclear designs mitigate this issue to a certain extent, but add other problems. The tremendous energy available in nuclear reactions has both good and bad sides, as all of these energy converting processes do. There are a couple of more steam cycle processes worth mentioning. At many locations around the world, hot water or steam is available by drilling into the Earth's crust. The steam, either naturally occurring or created by flashing hot water to steam by lowering its pressure, can be piped to a turbine and used to spin a generator. A binary cycle is also used, where hot water heats another fluid, which has a low boiling point, and the steam from that fluid drives a turbine. These geothermal cycle plants have been used for many years in many countries. Although geothermal resources are abundant, limitations from low temperatures, siting difficulties, and environmental issues restrict use to specialized cases. Geothermal units contribute less than 2% to worldwide electricity production. How many of you used a magnifying glass when you were a kid to heat things up? A piece of paper, a candy bar, and, yes, I admit it, an ant. Concentrated sunlight is very powerful. By focusing sunlight in various ways, liquids can be heated and produce steam to drive turbine generators. Several types of plants are in service or under testing. Some use parabolic concentrators to heat fluid piped through them, which is then used to produce steam. Others use a field of mirrors to concentrate sunlight on a tower with a fluid-containing vessel mounted on it, and there are other designs. Most designs incorporate some sort of storage system or supplementary firing to maintain production at night or during cloudy times. Technologically complex, solar thermal plants will be a part of future energy supplies, but probably a small part. Well, that's about it for steam power generation, but there are other ways to spin the magnet. Falling water has been used as a power source since the beginning of civilization. In the late 1800s, the basic equipment necessary to harness water power for electrical generation was developed. The Pelton wheel and Francis turbine, each used for particular supply conditions, allowed plants to be built which could generate usable amounts of electricity. However, one problem had to be overcome. Steam-powered AC had no trouble spinning magnets at high enough speeds that the cyclic nature of AC power was not visible. 50 or 60 cycles per second required a rotational speed of 3,000 or 3,600 RPM, easy for a steam turbine. Water wheels can't turn that fast. Their size and bulk made it impossible. This led to the development of Salient, or multiple-pole generators. Instead of one north and south in the magnet, like a steam turbine generator, a hydro generator has many poles, as many as necessary to produce the desired frequency based on the optimum rotation speed available from the source. Here's an example. A steam turbine rotating at 3,600 RPM with a two-pole magnet produces 60 cycles per second. Let's say our hydro resource can drive a water turbine at 720 RPM. How many poles would our magnet have to produce 60 cycles? There's a formula for computing the number, of course. It says the number of poles is equal to 120 times the frequency divided by the RPM. So in our example, we'd have 120 times 60 divided by 720, giving us 10 poles on our generator. The number of poles is adjusted up or down to suit the particular water conditions at each hydro site. The generators at large dam-based hydro stations may turn at 320 RPM with a 20-pole rotor. Small micro-hydro units run at 1,200 RPMs or higher, with proportionally fewer poles to produce 50 or 60 cycles, and everything in between. There are thousands of hydroelectric plants worldwide of all sizes. Some plants are even built inside self-contained bulbs driven by a propeller-like turbine and placed in areas of heavy current flow or tidal change. These units usually use a gearbox arrangement to attain high speeds for the needed frequency. Hydro plants produce over 16% of the world's electricity. Although they fit in the category of renewable energy and are generally considered non-polluting, they can have serious impacts. The reservoirs behind the dams cover large areas and displace populations when they are built. They can cover farmland or scenic resources. In tropical areas, methane emissions from reservoirs are comparable to the greenhouse gas emissions of a conventional fossil-fueled plant because of the anaerobic decomposition of organic material under the water. Wind has also been used to do work for thousands of years. Wind-driven spinning blades have pumped water and driven grain mills since medieval times and before. They can also be used to generate electricity. A lot of wind generators were installed in the American West before the Rural Electrification Administration funded the extension of transmission lines to rural areas. Modern wind generators are much larger and are being installed in clusters to take advantage of local wind conditions. The typical wind turbine uses a gearbox arrangement to increase the speed of the generator. Mechanisms are also included to control the pitch and direction of the blades. Over 50,000 utility-scale wind turbines are installed in the USA alone. Worldwide, wind energy currently, in 2016, supplies about 4% of electrical demand and is growing rapidly. Some projections call for wind to supply up to 30% of electrical demand by 2030, but objections to the visual impact of the towers and environmental concerns over noise and bird kill may blunt that growth. Internal combustion engines can, of course, be used to spin a generator. Many of us have portable units on hand for emergencies. I have one in my little cottage in the Michigan woods. Larger units are usually diesel-driven, and many diesel generating sets are used in places without connection to a power grid or as emergency power supply if the grid fails, as well as for more complex applications such as peak shaving, grid support, and export to the power grid. Their overall contribution to electrical supplies, however, is small. That pretty well covers generation by spinning magnets, fossil fuel, nuclear, geothermal, and solar steam cycles, plus water, wind, and internal combustion drivers, all in all accounting for over 98% of the world's electrical generation. That leaves us with the one other way to generate electricity on a large scale: photovoltaic or solar energy, the direct conversion of light rays into electricity. How does that work? Well, in the late 19th century, it was discovered that light rays could make charge move. It took a lot of experimentation, many stops and starts, and frankly, the fear of pollution and running out of fossil fuels to really kickstart things. But now solar technology is spreading rapidly. Most solar cells are still made from layers of silicon. If you'll remember, silicon is a semiconductor, an element that normally does not conduct electricity. The 4 electrons in its outermost shell bond to other silicon atoms in a regular crystalline pattern that results in no free electrons. However, if a bit of phosphorus is added to one layer of silicon, it changes things. Phosphorus has 5 electrons in its outermost shell. Now, when all the bonding's done, there are extra electrons about. This is called an N layer because it has those extra negative charges. Boron is added to the other layer. Boron has 3 electrons in its outer shell, meaning some of the silicon atoms won't be completely bonded. There will be holes. This is called the P layer because it contains the positive holes. When the 2 layers are joined, you'd normally expect the difference in charge to cause electrons to flow between them, but this doesn't happen. Instead, pairs of charges join to form an electronic barrier between the layers, preventing any flow from negative to positive. But expose the cell to light, and electrons in the P layer pick up enough energy that they are able to jump up to the N layer. This influx of negative charges causes a stream of electrons to flow out of the cell, making electrical current. The more light that shines, the more electrons jump up and the more current flows. A lot of research is being done to optimize the design of these solar cells, find materials that make the process work better, and increase the efficiency of the conversion. But the reality right now is that in many situations using solar energy makes economic sense. The idea of rooftop solar, with cells designed to look like conventional roofing material, feeding a battery bank large enough to power your house, is close to reality. This is an exciting time in the field of energy production from all sources. That was a survey of electrical generation. I hope you enjoyed it. Subscribe to my YouTube channel to see other videos in the series. Thanks for watching.